So we still have one more kind of equation to talk about in this section 6.6. We're going to look at a few examples of logarithmic equations, equations that involve logarithms, that have logarithms right in the original equation. And we're going to look at a couple different methods for solving. And the first method is just to isolate the log expression on one side, then rewrite in exponential form and solve. And one thing that's kind of strange about these log equations is, and eventually we'll see why, is that answers must be checked. It turns out that there's no way to avoid this problem where sometimes invalid solutions sneak through the process, and we'll see that along the way here somewhere. So let's go ahead and solve this equation. 2 log base 2 of x minus 5 equals -6. So this is very different from an exponential equation, right? We don't have x in an exponent. It doesn't look at all like the problems we've been doing. And I don't think we've had any example in this section where you've seen a log as part of the given equation right at the beginning. So these should kind of stand out and look different. So isolate the log expression. So log base 2 of x minus 5 is here. To isolate, we got to divide both sides by 2. I'm going to divide by 2 here. I'm going to divide by 2 here to cancel the 2. Then I have log base 2 of x minus 5 equals -3. Now, rewrite in exponential form. When we have the log isolated, we can go back to our very basic principle of log base b of, let's maybe say log base b of x equals y. That just means b to the y power equals x. That was our very first defining principle about what logs mean. That illustrates the fact that logs in exponential functions are inverses of each other. So here we would take the base 2 to the -3 power. That's got to equal what's inside the logarithm, x minus 5. Well, 2 to the -3 is 1 over 2 to the 3rd is x minus 5. That's just 1/8 is x minus 5. So if I add 5 to both sides, 1/8 plus 5 is equal to x. That's just, again, 5 is what, 40/8. So this is 41/8 is equal to x. I could also write it as a decimal. I could write it as a mixed number, 5 and 1/8. I'm going to leave it here as 41/8. Now, what the fine print in this section is going to be that we got to check our answer in the original equation. Sometimes we're going to see they don't work. Let's see what happens with this one. 2 log base 2 of 41/8 minus 5. Is that equal to -6? 2 log base 2. Now 41/8 minus 5 is just 41/8 minus 40/8 is going to be 1/8. So I have 1/8 inside parentheses. 2 log base 2 of 1/8. 1/8 is the same as 2 to the -3 power. And so I can simplify this log base 2 of 2 to the -3 because log base b of b to any power is always going to simplify to be that power, right? The log and the exponential function cancel each other off. So this is 2 times a -3 is equal to -6. Yeah, our answer checks out. So our check is, it's working here, no problem. So there's our answer. We were able to solve this equation, and we got an answer 41/8. Okay, let's do another. Number 2. And solve. 2 plus ln of x plus 2 equals 5. Sorry, that's kind of a sloppy ln. Let me write again. 2 plus ln of x plus 2 equals 5. And it's same process. We're still applying this method 1, where we're going to isolate the log expression, right? So here I want to subtract 2 from both sides to isolate. And my log expression is ln. Really, this just gives us a chance to talk about ln again right here. And so I have ln of x plus 2 equals 3. Once the log expression is isolated, then I have to rewrite in exponential form. Well, in order to rewrite this one in exponential form, you got to remember the relationship between log and e. I also could just rewrite this. ln is log base e of x plus 2 equals 3. So my base is e to the third power is equal to x plus 2. And notice there's just not that much to do at this point. I'm just going to subtract 2 from both sides. E to the third minus 2 is x. And that's my result. And here, I guess, let's get a decimal on here, because I think it's worth talking about how would you should have an e to the x button somewhere in your calculator. I have to use a shift key on mine. So I hit 3 shift to get an e to the x value. That's e to the third is 20 point something. I still got to subtract 2. So I get 18.0855 is approximately x as a decimal value. But we still need to check, just like the previous problem, because sometimes the wrong answer slips through. So take my equation, and I'm going to plug in my answer. Now what I think I got here is e to the third minus 2. So 2 plus ln of e to the third minus 2 plus 2. Is that equal to 5? Inside the ln I have 2, I have 2 plus inside the ln is just e to the third now. Is that equal to 5? Ln of e to the third, well, ln of e to any power is always that power. The ln and e cancel each other out. That's an illustration of the more general property log base b of b to the x is always x. That's true because log and exponentials are inverse functions. Here ln and e to the x are inverse functions. So this is 3. 2 plus 3 equals 5. It checks out. So again, my answer was fine. This result is what we get. There is one solution to this equation involving ln as a logarithm. Okay, we got one more that we're going to do. And here we go. I got this written out ahead of time. There's actually also just one more complication that we're going to bring up. We're going to have a second method for approaching these log equations. And I think this method isn't too hard to get down, because when it's available, it's pretty clear. Sometimes we can write each side of the equation as a single log, then set the expressions inside equal to each other and solve. This is kind of analogous to method 1 for exponential equations. But again, sometimes invalid answers sneak through, and we're going to have to check for that. Okay? So here, let's go ahead and solve this one. We're going to apply method 2 here. We're solving log x plus 1 equals log 6. I have just log written, so it's understood we're talking about log base 10. In each case, these are log base 10. And what I mean by write each side of the equation as a single log, if there's a way using the laws of exponents to combine, or not laws of exponents, laws of logarithms to combine, you can apply them. So here we can use the fact that log of A plus log of B is always going to be equal to log of A times B. I think on my yellow card I had that written with m's and n's, right? That was our product property that we're actually applying backwards. We're going backwards through those steps. And so I can say that the left-hand side is log of x times x plus 1 equals log of 6. Now, this is what I mean by write each side as a single log. I have log of one quantity equals log of another. So if log of, I guess I got to use some other letters here. I'll say C equals log of D. Then what we can do is we can just set C equal to D. What's inside has to be equal to each other, or you don't have to write that down, of course, each time. Here we can just say x times x plus 1 is equal to 6, and we can continue solving without the logs involved. So let's keep going. I'm going to distribute. X times x is x squared plus x equals 6. It looks like a quadratic. X squared plus x minus 6 equals 0. I'm going to try factoring this quadratic, x and x. Let's see, minus 6, but I want a plus x in the middle. I think plus 3 minus 2. I think I can factor. And check that out. And so x plus 3 equals 0, or x minus 2 equals 0. X is equal to negative 3, or x is equal to 2. So I have these two solutions, right? And we got to check them. And first, let's we can only check one at a time. Let's check x equals negative 3. If I plug into the original equation, which is up there, I would have log of negative 3 plus log of negative 3 plus 1. Is that equal to log of 6? And now we got trouble. This is trouble because there's no way to take log of negative 3. So here's finally an illustration of where this process kind of breaks down in a sense. It gives us a solution that really isn't a solution. It doesn't check out. And that's what we mean back in our description of the method, where we say answers must be checked, invalid solutions can sneak through. Sometimes. We did 3 problems. This is the first problem where this has occurred. And basically we got to throw away that negative 3. That's not really a solution. What about x equals 2? Is that one going to work? Is log 2 plus log 2 plus 1, is that equal to log 6? Log 2 plus log 3, is that equal to log 6? Now here, no negatives. inside the log, right? And log2 plus log6 has to be equal to log of 2 times 3. And so log of 6 equals log of 6. This one checks out. So 2 does check out. We did get just one solution to this equation. There's just one solution, but at least we got one. Okay, and that's our last log example. Again, maybe I'll try to back out a little bit so we can see the whole process here for this problem in one shot. And that's it for exponential and log equations. What we'll move to next are applications. And the applications of exponential and log functions are really interesting, I think. I think you're going to enjoy the next section.